3 times 2/3 is 2, so this is 2x to the negative 1/3, and then this is just minus 3. Right. Well, even this is sort of, well, let's see, what should we do? This might strike you as a little bit silly, but I think it's actually good. Let's factor out x to the negative 1/3. And if I factor out x to the negative 1/3, I'm left with 2 minus 3. Well, x to the what times x to the negative 1/3 is x to the 0. X to the 0 is, because x to the 0 is 1, this is x to the 1/3. Let's see, have I done that correctly? Sure, I have. And so, factoring out now a negative 3, that means I'm going to write this as x to the negative 1/3 times, I take out a negative 3, leaving me with cube root of x minus 2/3. Yeah. Why would I go to these strange lengths to write this in such an obscure way? Because when it comes to making my sign chart for this, this might be the simplest way to do this, although I could be talked into it not being the simplest way. Well, okay, let's just keep writing, let's just keep going. So this is negative 3 times cube root x minus 2/3. Just hope I'm doing that right. Yeah, I am. Over cube root x is the form of the first derivative that I'm going to use in order to try to graph this function. And believe it or not, that's the best form. Okay, moving on to take the second derivative, which I think is a little bit easier. What's the second derivative? Well, I go back to this version to differentiate, and I get negative 2/3 x to the negative 4/3, and then derivative of negative 3 is 0. Alright, so that was pretty easy. This is going to be negative 2 over 3x to the 4/3. And good. Well, that's it. Now I can make the sign charts sort of immediately. I'll do them up here. What's my sign chart for f? Well, sign chart for f, I see, and this is why I was talking about this being such a useful representation, I see from this representation a couple things. First of all, that when x is 1, cube root of 1 is 1, so this will be 0. So 1 is definitely a relevant number. And it's a 0 of the function. And 0 is also relevant, although anything to the 2/3 is positive. That's just a fact. So you can either include 0 or not. I'll include it in this case, but there's no sign change at 0. And so there's only a sign change at 1. Okay, if you take the cube root of something bigger than 1, it's bigger than 1. And if you take the cube root of something less than 1, it's less than 1. Therefore, this is kind of like more advanced than what we did in pre-calc C. You have to be such an expert on making sign charts for polynomials that now we are making sign charts for non-polynomials, but the logic is exactly the same. Whether or not cube root x minus 1 is positive or negative depends on whether x is bigger than 1 or less than 1. So this factor changes sign at x equals 1, but then there's also this negative 3 up here. This is always positive, so if you put that all together, that tells you that this function is going to look like this, and is going to go from positive to negative at x equals 1. And so this function is going to be positive, positive, negative. Now, and I suppose you could have seen that. You could have seen, I suppose, that x equals 1 is a root, and that x equals 0 is a root. But to me, this very obscure steps that we took to factor this seems like the best way to make the sign chart for this function, which is certainly important when it comes to graphing it. Okay, what about the first derivative? So directly underneath, I will make a sign chart for the first derivative. Okay, and here I get complicated things, right? It seems that if I take the cube root of something positive, it's positive. If I take the cube root of something negative, it's negative. So the denominator will change sign at 0. But then there's also going to be a sign change up here because, well, it's the exact same logic, just harder now. If I take the cube root of something more than, when is this going to change sign? This is going to change sign at, this will be positive when x is bigger than 8/27. If x is bigger than 8/27, I'll put that here, 8/27, then the cube root of x will be bigger than 2/3, and hence this factor will be positive. Okay, so advanced algebra analysis tells you that this expression, this one in parentheses alone, is going to change sign from negative to positive at x equals 8/27, if you're following that. And so you have to be so experienced with making sign charts for polynomials that you can see this complicated thing here in the box and basically think of it like quadratic-y. That's why I made up that phrase kind of quadratic-y, because this is quadratic-y in the sense that this term changes sign, you're multiplying a bunch of things, one of which is changing sign from negative to positive at 0, and the other of which is changing sign from negative to positive at 8/27. And there's a leading coefficient of -3, which means that the end behavior for this entire expression is like this, and so it goes negative, positive, negative. And indeed, assuming I haven't made a mistake, I now know that my function is decreasing on the interval from -infinity to 0, increasing on the interval from 0 to 8/27, and decreasing on the interval from 8/27 to infinity. I mean, the alternative is, what's the alternative? I guess the alternative is, instead of doing this fancy factoring and fancy sign charts making, well, I think this is the best thing to do. You could always just set this, I mean, I'll do it down here. An alternative, if you think this is sort of too hard or something, you know, an alternative scenario is more maybe kid-friendly or something, is just to solve this equation. So, you know, 2 over cube root x minus 3, that's the first derivative after all, equals 0. Well, what do I notice right off the bat? I notice that 0 is a critical point, so that's something, because that makes the derivative undefined there. And actually that's even worth mentioning that f prime of 0 is undefined. And okay, abusing notation a little bit, I'll even just say, you know, infinity, or maybe I'll write plus or minus infinity, because in fact, what's true about the derivative of f at 0, if you try to plug 0 into the derivative, you get like either positive infinity or negative infinity, which means actually something. It means that the slope of the tangent line to this function is like infinity near x equals 0. In other words, f has a vertical tangent, a so-called vertical tangent at x equals 0. This is definitely worth mentioning. And the other question is, well, what are the other critical points besides 0? And now you can just solve this problem in a more traditional way. So 2 over cube root x equals 3, and then that can be rewritten as cube root x equals 2/3. And now the way you solve this problem is by cubing both sides, and that gives you x equals 8/27. So that's how you learn that 8/27 is a critical number. And so we've recovered the same information that I got doing it my way, that there is a critical number at 0 and a critical number at 8/27. But doing it this way doesn't help you make the sign chart for the first derivative, and that's what I want ultimately. So this seems like the best way. The only thing you could do is you could know that there were critical numbers, and then you could do the method of last resort is you just plug in test points. So you just plug some negative number into the first derivative and see that you will get something negative. Plug something between 0 and 8/27 in, like, I don't know, 1/27 or something like that. And the cube root of that is 1/3. And so, but it's in the denominator, so this becomes 6 minus 3 is 3, which is positive. And then you could plug in something bigger than 8/27, like 1, and you get -1. That's really not that bad. So okay, if you can't handle this complicated algebra factoring that I'm fond of, you can always just set it equal to 0, solve for the critical points, notice when it's undefined, start to make your number line and just plug a number in from each interval, and then that's another way of getting the correct sign chart. Okay, the second derivative to finish this problem is -2/3 x to the 4/3. Well, once again, you can take the cube root of anything, and if you take the cube root of something positive, it's positive, the cube root of something negative is negative, but then when you raise that to the 4th power, it becomes automatically positive. So you just have to know that x to the 4/3 is positive always. Since x to the 4/3 is positive always, this second derivative is just always negative. And I'll just write negative. And therefore, this function is concave down. Okay, what I didn't do in the previous two problems, because I just forgot or I just didn't feel like it, but I'll do it now, is the whole thing which I taught in the videos about how to do this curve sketching, which is that after you make the sign chart for the first derivative and the sign chart for the second derivative, then you combine that information into one big chart. So this is 0, and this is 8/27. And then what you do is you draw in each of these intervals a sort of generic function which is both decreasing and concave down. So what does it mean to be decreasing and concave down? Well, no, concave down, hands on the elephant, so that means tangent lines lie above the curve. And if you're decreasing in concave down, then you look something like this. And now if you're increasing concave down, then you look something like this. And if you're decreasing concave down, well, you again look something like this. Is that right? No, sorry, decreasing concave down. So you look something like this. Okay, and yeah, all right. Now, without further ado, we graph this function. So let's go. And yeah. Cha and cha. And okay, I plug in 0, I get 0. I plug in 1, I get 0. I plug in 8/27, it's like a third roughly, 8/27, and I get, okay, do I feel like doing it? I guess I do. The cube root of 8/27 is 2/3, as we've seen. But then squared is 4/9. So 4/9 times 3 is, it's too hard for me to do in my head, 4/9 times 3 is 4/3. So that's 4/3, but then minus 3 times 8/27 is just 8/9. So minus 8/9. So that's 12/9 minus 8/9 is 4/9. Okay, so indeed, no, it wasn't too bad. Indeed, I have a relative max at 8/27, 4/9. That's what this is telling me, right? Relative max at x equals 8/27 because the derivative changes from positive to negative. And in fact, 8/27 is a number that when I plug it into the function gives me the derivative gives me 0. So I know, I'll put a little dotted line here, I know that I have a horizontal tangent at y equals 4/9. But this other point of interest on the sign chart for the first derivative is 0. The derivative changes from negative to positive at 0, which tells me that 0 is a relative min. But it's a strange kind of relative min because, as we mentioned, the first derivative is undefined there. And so in fact it's one of these relative minima where the tangent line, I'm using green now, to draw this tangent line is a vertical. Okay, and now that I've done all that, I put it all together in one final step. So I'll graph this function in purple, and I'm using, I suppose, everything. But really I'm using the two f number lines. The f on the top, which told me using pre-calculus methods only, that this function is positive until 1 and then negative thereafter. And this sign chart, which is telling me, which is combining both the increasing, decreasing aspects of the function and the concavity. And what this is all telling me is that this function is decreasing concave down and positive from negative infinity to 0, and that there's a vertical tangent at x equals 0, which means it's kind of got one of these sharp type things. Chop. And then, what happens here at x equals 0, as soon as I hit 0, now the function is increasing concave down and staying positive the entire time. And then when I hit 8/27, I have a relative max. So now my function is decreasing concave down. And then at 1, nothing changes on the graph shape-wise, but 1 is where the function crosses and becomes negative. And so there it is. That is the graph of this function. And once again, I hate to keep saying this, but if you were very good at pre-calculus graph making, you could have known almost all of this because, well, we made this sign chart for f based only on pre-calculus knowledge, and now you can see that x to the 2/3 is, after all, bird. And we see that this function is locally bird here at 0. And sure, locally bird at 0 this function is, and here it's going to just be, that's interesting, I guess it's going to be kind of, it's going to act like cube root of 1, which is just 1, so it's sort of indistinguishable. Yeah, anyway, when you, yeah, the cube root of 1 is approximately 1, so it's not gonna, this is kind of hard to say about. But anyway, this kind of graph, you could have probably, if I gave you a lot of time and thought, guessed that this was the correct graph to this function, even without any calculus. What the calculus does is make all of it easier, and also, of course, I need calculus to know that there's this relative max at x equals 8/27. Okay, 3 down, 2 to go. Time are we on here? Yeah. Okay, 41. Oh man, I hesitate to do this problem. I know this problem, it sucks. Let's go. G of t equals 10 over 1 plus 4 e to the negative t. Okay, you graphed problems like this in pre-calc B last year. This is a logistic curve. Very much, you know, in the news, these logistic curves, being the curves which describe functions which increase exponentially up to a point, say some disease spreading through the population, but then because there are only a finite number of people that can catch the disease, if 100% of the population is going to get it, then there will be sort of asymptotic behavior as the last few people get it. So these are the people who are like, you know, wiping down all their groceries and like literally never leaving their house ever. These were the people partying at spring break. And what you were told in pre-calc B simply, I think Kirk simply just told you, fact, this function is going to kind of look like this, and at the halfway point, so this is often called M, the value of the horizontal asymptote on the right hand side, that there's this sort of m over 2 point, and in fact, I think the first time you ever heard the term point of inflection, it's possible that I think vaguely I recall that Kirk just calls it a point of inflection in Precalc B, referring to this point on the logistic curve where the rate of growth is steepest, which occurs at the halfway point height-wise. And in fact, it's going to be where this function goes from being concave up to concave down. So the function is still increasing throughout its entire domain. This function is always increasing. But the point of inflection is the rate at which, well, it's the point where the rate of increase goes from increasing to decreasing. Characteristic of an exponential function is that not only do they increase, but they increase at an increasing rate. And so here this function acts like an exponential, increasing at an increasing rate, and then when we hit the point of inflection, the function starts increasing at a decreasing rate. So it decreases slower and slower. To me, these are just basic facts of life without which you can't understand any graphical analysis. So I think it's good that you know calculus now. All right, we could just stop it there. Of course, without actually doing any calculus, you just had to take Kirk's word for it, or your pre-calculus teacher's word, that logistic curves behave this way. So now, to take a generic example of a logistic curve, we can simply do a lot of calculus and we can find out all these things. So let's go, and I suppose the first thing to observe is that, well, there's a lot of things to observe, but if I rewrite this function without negative exponents, then it's really just 10 over 1 plus 4 over e to the t. And so there are many things to observe about this function. I think maybe I'll do it over here. What's one observation? One observation is, well, e to the anything is positive. And so if e to the anything is positive, this will be positive, the denominator will be positive, the numerator is positive. So this function is always positive. So fact, g of t is always positive, so there are no roots. That's important to know. I guess I can always just plug in 0. What do I get? E to the 0 is 1, so I get 5 on the bottom. So g of 0 is 2. That's nice. I can also do end behavior. So what's the limit as x approaches infinity of this g function? Well, we can just do this. Let's see. As x approaches infinity, that's like infinity. So 4 over huge is basically 0. Yeah. So this is going to be a tiny positive number, and if this is a tiny positive number, then when I get 10 over 1 plus a tiny positive, then that is really going to be 10 over a number which is a tiny bit more than 1, so I'll call it 1 plus. Well, if you divide 10 by 1, of course you get 10, but if you divide 10 by a little bit more than 1, you get a little bit less than 10. So the answer to this limit is 10, but for purposes of graphing, it's nice to know that in fact, as x approaches infinity, the values are going to be a tiny bit less than 10. Okay, what's the limit as x approaches negative infinity? Well, now maybe the simplest thing to do is to use the original version, because if x is like negative, if t is like negative a million, yeah, these should all be t's, I suppose, because that's our variable for whatever reason. So that's going to be huge down here. So this is 10 over a gigantic positive number. So this is in fact going to be 0, and always a little bit more than 0. Okay, so we've confirmed the things I sort of told you already were going to happen, which is that we're going to have a horizontal asymptote of y equals 0, which is going to be relevant for the left end behavior, and a horizontal asymptote of y equals 10, which is relevant to the right end behavior. So kind of almost already, well, I didn't run out of space. Maybe I'm going to make my graph here. And what we see is that at x equals, or maybe I'll use a different color. At y equals 10, I will have a horizontal asymptote, and at y equals 0, I will have a horizontal asymptote. And also, when I plug 0 into this function, I get back 2. So I'll put a 2 right there. And now what's left? Well, what's left is everything else. And I think I've run out of pre-calculus that I can do. And now I just have to do some calculus. So let's go. First, I'll rewrite this function in a way that makes it easier to differentiate. I don't want to use the quotient rule here because the numerator derivative is just 0. So I think the best thing to do is to think of this as 10 times 1 plus 4e to the negative t to the negative 1, and just put our confidence in the chain rule. Okay, let's go. The derivative of g is negative 10, 1 plus 4e to the negative t. So what's the derivative? Okay, so it's 10 times, what's the derivative of something to the negative 1? Negative 1 something to the negative 2, back inside for the derivative of that something. And what is the derivative of 1 plus 4e to the negative t? The derivative of 1 is 0, and the derivative of 4e to the negative t is 4. And the derivative of e to the negative t is e to the negative t back inside negative 1. So this becomes negative 4e to the negative t. And so, maybe this isn't so bad. What do we end up with? This negative cancels that negative. And I end up with 40. Well, so 40 on the top. And this e to the negative t, we might as well stick it on the bottom. So that's e to the t. And then what's here is 1 plus 4e to the negative t squared. So that's actually wasn't too bad. That's my first derivative. Okay, now I guess here's where it's terrible. I really just don't want to do this, but too bad. Let's do the second derivative. What is the second derivative? I have to use the product rule combined with the chain rule. So let me just write the first derivative one more time as 40e to the negative t times 1 plus 4e to the negative t to the negative 2. This to me is the form which makes it easiest to differentiate. And now we're just going to go. So, using the product rule and the chain rule. So the derivative of the first, which is going to be negative 40e to the negative t, because of the chain rule, hence the negative. So the first times the second, so 1 plus 4e to the negative t to the negative 2, plus the first, so that's 40e to the negative t times the derivative of the second, and the derivative of the second is negative 2, 1 plus 4e to the negative t, to the negative 3, something back inside for the derivative of 1 plus 4e to the negative t, which is negative 4e to the negative t. Yikes. What can I do with all this mess? Well, let's just go. I'll have one more line of combining like terms. So I get negative, or simplifying, so negative 40e to the negative t times 1 plus 4e to the negative t to the negative 2 plus, now I have a negative and a negative, so that's going to cancel. So I'm just going to get, I'll just call it 8 times 40 e to the negative t and another e to the negative t, so that's e to the negative 2t times, took care of the 40, took care of the 8, yeah, times 1 plus 4e to the negative t to the negative 3. And now, sure. I'm getting a little skeptical, but okay. Hopefully I didn't make a mistake. Now, let me factor out 1 plus 4e to the negative t to the negative 3, and also I will take out a 4 e to the negative t. So 40e to the negative t I take out, and I take out a 1 plus 4 e to the negative t cubed, leaving me with negative, I took out, that should be negative 3, I took out 1 plus 4e to the negative t to the negative 3, so I'm left with just one of these 1 plus 4e to the negative t's left over. Then I took out 40, so I'm left with, and then plus 8e to the negative t is what I'm left with. The algebra skills required to do these problems are just so high, it's really ridiculous. But there it is. Okay, so what's all that? It's going to be, if I can simplify what's inside here in one step in my head, it's going to be 4 e to the negative t minus 1. So what I really get after all this is 4e to the negative t minus 1 over, and there's also a 40 out here, so 40 times that, and then the bottom, e to the t, and 1 plus 4e to the negative t cubed. And I'm not even going to double check this because I'll find out in a minute whether I'm right or wrong, because I already know what's supposed to happen. So, e to the t, always positive. This expression, always positive, so when you cube it, it's always positive as well. So the only thing that I need to know is, when is this numerator positive? So over here, I'll sort of solve for myself a little question. When is 4e to the negative t minus 1 positive? Answer, when 4 over e to the t is bigger than 1, and since e to the t is always positive, that's equivalent to saying when is e to the t, well, when is 4 bigger than e to the t, and so that is going to happen, when is e to the t less than 4? That's going to happen when ln of 4 is greater than t. So when t is less than ln 4. Okay, so if you plug in a number less than ln 4, then, which kind of makes sense, then when you take the e to the t of it, it's going to be less than 4, which when multiplied by 4 is less than 1. Sorry, when you put,